It's my pleasure to introduce one of our new members for our Thursday seminar today, Carol Cuesta-Lazaro. Carol grew up in Spain, or at least you went to undergrad in Spain, and studied at Universidad Autónoma de Madrid before doing, and then went on to a master's at Heidelberg and a PhD in Durham, during which she worked on many topics in computational cosmology. Also, something happened in 2020 that sparked her interest in epidemiology. I'm not quite sure what that could have been, but she also worked with the NHS during that time. And then afterwards, for her first postdoc, went to the NSF's Artificial Intelligence and Fundamental Interactions Institute between MIT and Harvard, where she really spearheaded and did a lot of very interesting work at this intersection of computational cosmology and AI. So very glad that she's here today to tell us about her latest work on generative solutions for cosmic problems. And there's still time on her schedule if you would like to chat today. She'll still be around, but not for too long, because I hear she might be moving in the spring term. Yeah, definitely make sure to chat with Carol. Let's get the kids afterwards.
Thank you very much, Nick. Yeah, so I'll be around, so feel free to come up to my office anytime. At half the time, I'm in the Baryonic Institute, so in New York, but I'll be around half the time. Very happy to chat about anything related to machine learning and astrophysics. Actually, the talk today is going to be half on cosmology, mostly on field inference and how machine learning can help us scale it up. But half is more on general problems in astrophysics that I think interesting machine learning solutions could help us disentangle. That is more experimental, so it's the stuff I'm working on right now. Hopefully, could spark some conversations with people here. Okay, first of all, why are generative models something we should pay attention to? Well, I will say that probabilistic machine learning has made high-dimensional inference really attractive. And this is one of my favorite examples called Genie2, what people call a world model. So these are models that can sample a playable world, giving a text prompt. So here you're telling the model, can you create a game where I can be a boat in, I don't know, New Jersey, moving in a lake, right? And then a human can actually control that boat and play around in that world. And you can see the diversity of worlds that you can actually generate with these kind of models. So this is extremely high-dimensional inference if you think about it. You have, let's say, 1,000 times 1,000 pixels, also as a function of time, and you're controlling it with text, right? So the probability distribution being learned is extremely high-dimensional. And the correlation between the world and the prompt is actually pretty loose, right? So the prompt is a very abstract representation of the world you're creating. So this is extremely impressive. Now, this is from about 6 months ago, which in machine learning means it's extremely outdated. There's already a new version called Genie3. That is even more impressive, right? So this is the same world being generated by Genie2 versus Genie3. So much higher resolution. And something these models struggle with is consistency, which obviously is important for science, right? So if the player goes around that world, comes back, the world has changed extremely, right? So that's not so true for Genie3, right? So people are getting better and making these models more consistent. And in particularly more like physically consistent, in the sense that if I throw a ball, actually the way that ball falls, it does make physical sense. So these models are improving at a rate that is extremely impressive. Now, this has, of course, also has implications in sciences, and in particular in drug discovery. So I would say that is the area where machine learning has had most impact in the sciences. And the idea is that you can basically produce drugs given some properties that you're after. Now, this used to be really, really expensive because you had to verify it in the lab, whereas these models are becoming so good that people are actually starting to trust them. So you can avoid having to develop this drug in the lab to really verify it has that property. Now, it's okay if they make mistakes because they can actually pair them up with like fully automated wet labs, right? Where it can be synthesized and feed back into the model so that it can learn from its own mistakes. And that's an important property that is hard to reproduce in Astro. Is there a question?
Yeah, so for the Genie thing, how should I be thinking of this? Because if there's not persistence based in Genie2, then it must not be generating like a wireframe of the world. So is it that it's just generating an image at every single frame and listening to user input, or?
No, it actually generates one video. Well, let's say they first take the entire video at training time, compress it into a smaller dimensional representation, and then generate the smaller dimensional representations. But when you decode them back to the original video, you might lose some self-consistency. If this compression you've done in the first place is lossy, which it always is, right? Yeah, The paper's not really out, so this is more like a blog post I put out because, yeah, these days apparently it's not in fashion to actually write papers about what you do in machine learning. So it's very hard to tell what it's actually that they did to improve it. Hopefully one day we will know, but it definitely is much better at consistency across time. Probably working on this like compression, decompression, making sure it's consistent is the way to go. Yeah, feel free to ask questions at any time. Yeah, the most interactive, the better. Thanks. Right, but in terms of astrophysics, why do I think this could be helpful? Well, first of all, we're going to have more data than ever, so we should think about what we want to do with it. And in particular, some people call this like the era of like big data cosmology, right? What we don't say so often is that the era of big one-dimensional data cosmology, right? Because we never actually analyze those data sets like beautifully 3D clustering of galaxies. What we do is compress them into one-dimensional star statistics, like 2-point functions, power spectra, etc., and analyze those like lossy compressions of the field. And also, I think machine learning will help us do this better, right? But beyond that, there's a lot that we tend to forget about, is that these are all astrophysical probes, right? So if we really want to make the most of these data sets, we'll have to care more deeply about the astrophysics involved. And again, I think machine learning can help us do that. The hope is that by having all these like multi-wavelength observations, we can actually learn something about both cosmology and astrophysics if we think about this more holistic picture. Now, what am I actually going to talk about? Well, first of all, I will talk about how we can use generative models to scale field-level inference in cosmology. If you don't know what that means, we'll go step by step. And then on the second part, I will talk more about ideas in representational learning. So how we can use these generative models to learn interesting representations of the world in astrophysics from observations directly, and how we can manipulate them to make them more useful. Okay, so field-level inference, what do I mean by this? So in cosmology, the large-scale structure, we can think of an observed galaxy distribution like, well, DESI observed, right? Like 3D point out of galaxies over a very large volume of the universe. And what we would like to do is find a set of initial conditions in the very early universe and a set of cosmological parameters that govern the evolution of those initial conditions into what we see today. So we would like to see, can we actually infer the initial conditions, so the random seed of our universe, instead of looking at possible universes that could be compatible with ours by marginalizing over initial conditions, which is what we usually do in 2-point functions, right? We actually want to infer those initial conditions to find the random seed that will generate the structure that we have around us. So that it's not just compatible at the level of summary statistics, but that we can reproduce the local universe, for instance, or the clusters that we have around us in a simulation. It means that you could have like a digital twin of our universe without cosmic variance, right? Reducing cosmic variance as much as you can from observations. Now, ideally, what we want is also to get some measure of uncertainty on those, right? We want to sample the posterior of the initial conditions and cosmological parameters given this observed galaxy density field.
Can I just ask philosophically, I mean, the point about no cosmic variance, our cosmological model has cosmic variance, right? You have a set of parameters that can produce a lot of different universes. We're just one of them. And so you can simulate the one that we're in, but how is this approach going to avoid over-interpreting the phases as something about the cosmological parameters?
Right, now that's totally possible, right? If you have the wrong forward model, you could definitely put model misspecification in your phases. Now, what I would argue is that this gives you a tool to verify this in very extreme cases. And we'll talk more about that, but now you actually have constrained simulations that you can cross-correlate with other observables and check whether you can actually predict those observables that you didn't use for fitting, right? So cross-validation becomes, you can make very precise tests of the model, right, without cosmic variance, which is very interesting.
Okay, thanks.
Right, so the motivation that people usually give for doing field-level inference is obtaining optimal constraints on cosmological parameters. So if you did this, you wouldn't have to worry about what summary statistics that I use for my field, kind of capture all the information in my observed galaxy clustering by doing field-level inference. Now, I'm not sure I agree with this. I think if this is all you care about, I'm not sure you really need to sample 10 to the 9 extra parameters in the initial conditions to obtain optimal cosmological constraint. Okay. In particularly, now that we can use machine learning to overcome this issue. So I think in the past, this was true that maybe if you cared about optimal cosmological constraints, all you could do is sample the initial conditions, but this is not true anymore. So this is the first thing we'll talk about. What are the alternatives if you only care about constraining cosmology? So first of all, you can learn a marginal likelihood. So here you have P of x given theta, so probability of a galaxy distribution given some parameters that you want to constrain. Now, what we do usually is solve this integral by Monte Carlo sampling, right? By sampling the initial conditions. But Z will be the initial conditions here, extremely high dimensional, so very hard to sample. But this is the way we get to the marginal likelihood, right? By sampling these initial conditions. Now, why I'm arguing is that we can learn this directly from samples from simulations. So we don't have to actually do this marginalization explicitly. We don't have to sample it. We can use machine learning to take a shortcut here and learn directly the marginal likelihood, which analytically would be impossible. And if you want to make it tractable, you'll have to sample. So to avoid that, you can directly learn the marginal likelihood. The alternative is also to learn an optimal compression of your density field. So again, you can use machine learning to take your high dimensional density fields and learn a lower dimensional representation that has the maximum mutual information with your cosmological parameters, right? So basically finding optimal compressions of your fields. Again, these two methods will rely on the fact that we can simulate these processes, so we can learn these from samples from our simulations. So this is what we usually call an explicit likelihood, where we're actually learning a likelihood, although it's being marginalized by initial conditions. Whereas the second one, you could refer to as implicit likelihood, because the likelihood is never actually directly used, right? You're learning the posterior directly with your model.
For your point about learning the marginalized likelihood, how should I think about this? Because one way I could think about this is to say, okay, well, I can just separate, if it is possible to separate the two P's, then I can learn them independently. In some way, I can learn their structure. But there's, very naively, I would expect there's some kind of question about just how much information do you have, right? And so if it's not true that you can get those two little P's are separable inside of the integral, then you do need to, I would expect, you do need to just have enough information to learn the structure of all of this. And so in what way then is it, in what way is machine learning not just doing a different approach to Monte Carlos?
It is somehow doing a different approach to multiple sampling, using an amortized way, meaning that you're paying the cost of sampling at training time. So during training, we will have samples where we vary Z and theta, but then after training, we can amortize the sampling, right? So now you give me any new sample and I don't actually have to run the entire chain, right? I can get independent samples within seconds. But it is somehow happening during training. Right, so first of all, what do we mean by generative models? So I think it's useful to have a picture in mind where usually starting from a set of samples, right? It could be samples from our simulator, samples from observed data sets. Here's a very popular two-dimensional example called the two-moon problem. So here you have the positions of particles in 2D. And what we're going to do is we're going to try and learn a parametric PDF for these samples, right? So P of phi are going to be some free parameters, which will actually be a neural network that capture the underlying probability distribution. And we will learn to fit these parameters phi from samples directly. And the idea is that you can directly maximize the likelihood of the training samples. So you just find the phi parameters that maximize the likelihood of your training samples. Now, what you can do with this train model is you can both generate novel samples, right? So this is a model trained on human faces. You can generate new human faces that were not part of the same data set, but that live in the same manifold. But you can also evaluate probabilities. So if your model is well calibrated, it should hopefully tell you that a human face is pretty likely, whereas a human with 3 legs should be less likely, right? If it's well calibrated, hopefully. So this means that we can use a generative model like a simulator in a way. So a simulator can definitely generate novel samples, right? I can vary my initial conditions, cosmological parameters, create a new simulation. What a simulator cannot do is evaluate probabilities. So a simulator has no idea of how the manifold of possible solutions look like, right? If I generate a new simulation, I can't ask my simulators to tell me how likely that simulation was, right? Whereas a generative model can actually do that. So that means we can use them as fast emulators, or something pretty expensive to run, but also for inference, right? So the inference
how likely it is in the context of the examples that were presented. So it's actually learning about the training set, how similar to the training set. And okay, if it's real data in the world, perhaps makes sense, but if it's things that you generated, the parameters that you pick, is what determines these, right? So,
Right, yeah, sure, you need a big enough training set, but within that training set, you can learn the manifold structure, right? Like you can generate a new sample and still get a sense of how likely it is. Like, why do you think natural images are different from?
no, because no, natural images maybe are trained with natural examples. So, but here you would be training it with some made up thing. That,
Right, we'll talk about that a lot, for sure, that is for sure a problem.
Just curious, is there some sort of like theoretical definition of what it means for a training set to be good enough? Or some sort of theoretical criterion that people have derived in the community? Or is this just sort of like, I know it when I see it, but there's no sharp sense in which a training set is good enough or not?
Yeah, that's very hard to tell from a theoretical perspective. I think for very simple models, people have been able to at least make some statements, but for these kind of models, no. But there's been some interesting examples where you take a huge data set and make two non-overlapping splits of that data set, train two separate models, and shown that if you increase the data set size, the probabilistic model that you get, like the P that you get, is actually the same. It was trained with two non-overlapping sets, right? So that's an interesting. So there's interesting empirical results, but yeah, not much known theoretically.
And do the like weights of these models converge to the same
No,
values?
the weights don't converge to the same values. I mean, there's many things that play into this, right? But you end up with the same probability distribution.
But not in the mathematical sense, sorry.
No, no, empirically, yeah.
So maybe you'll talk about this, but in terms of the weights, is there a way to, I'm gonna use a geometric term, to like rotate the weights from one model into, some one instance of training to another one, and we can learn through those rotations or what transformations is going on?
Yeah, no, I don't think that's quite that simple. There are some symmetries in the sense that in the same layer, you can swap neurons and that should make no difference. So there are symmetries that people have exploited, but I'm not sure we have learned much from that.
Like in some sense, it must be like a congruence class, like there's some similarity relation between this, or this draw of weights.
I think in some examples with convolutional neural networks, this guy Brice Menard was talking about this and had more claims that he can understand better. Anyway, so he explained to me and I'm very good. But I remember this. So,
right, usually these things have been shown to work on like very toy modelish examples. In like bigger models, it's very hard to say anything about that. Right, so I really like this picture to conceptualize what a genetic model is actually doing. And there's a quote from Yansong talking about how creating noise from data is easy, and we've all done it once or different times. But like creating data from noise is actually what you're doing in genetic modeling, right? So the idea is you're going to start from a base distribution that is ideally simple in a way that you can sample from it, but also evaluate probabilities of. Which, yeah, there's not many distributions where we can actually evaluate probabilities of, right? So kind of restricting. Then we're going to learn to bridge it to our data distribution, right? So in 1D, this would be our target distribution and a simple Gaussian-based distribution. And we're going to learn paths that connect the two. This could be deterministic or stochastic, right? So, and that will define like different families of generative models. But the idea is that you'll have some distribution X naught that you can sample from, and then you're going to match it, like bridge it to your data distribution. So this is what you do during training. A simple ODE model, so a deterministic model that will start from a sample from the base distribution to the target distribution in continuous time will look like something like this, right? So it's an ODE where your velocity model will be a neural network with some parameters phi, right? So it will take your X naught samples and learn a velocity field that takes you into your data distribution.
so we should think of the time as the layer of network.
Not really, not really. So time is really just a construct to go from Like the layers of a neural network, so the neural network is predicting the velocity field at any given time.
What is the time?
So
Or you can output this model has a time that you can see what's happening as one parameter at the end or something. You know.
right, so only the endpoints are relevant, right? So you only define the endpoints. The path is learned, and it's not actually, it doesn't have any physical meaning, right? Now, it is true that you could think about this as discretized layers of your neural network, and this is the continuous limit. So if you stack infinitely many neural networks, you'll get this continuous limit. And now you can parameterize your neural network as a function of time instead of having separate layers. So you can make much smaller models this way. That's the reason why you have this like continuous time formulation. But also the other reason is because if you want to compute probabilities, now you have this continuity equation, right? Because P has to be normalized at any given time. So you have this continuity equation for the probability of X at any given time. That is given by the divergence of your learned velocity field. So now if I want to compute probabilities, it's actually very easy, right? So I can compute P of X1, given that I know P of X0. Okay. Which if you don't do this continuous time trick, is more involved. You have to have some, so the velocity field, for instance, has to be invertible for this to work, like this is what normalizing flows do. But if you don't want to have to do that, then the continuous time formulation helps you with the ODE.
But then you are solving an ODE. This thing is
You're solving ODE. Yeah, so it's invertible by definition, right? Whereas if you don't write it as a continuous time, it becomes a bit more involved. And you have to restrict your architecture. Whereas here, your architecture could be anything, and this always is invertible.
I think about this as like if I run a stable diffusion model that goes through different levels of fuzziness, should I think about that going from the right to left here? Or
What do you mean by different levels of fuzziness?
when I run the stable diffusion model, it starts with a very blurry thing.
Yeah, exactly. Yeah, so if you think about it, you start usually from a Gaussian distribution with white noise, and then you go into your data distribution. Now, because the power spectrum of white noise is like this, and natural images actually looks like a cosmological field, then you always first start with the large scales and then infill the small scales.
But if I think about it this way, then it is kind of like iteratively saying like, okay, I go from X naught to a little bit and then to a little bit.
That's right. Yes, you're kind of trying to find the direction slowly instead of a water. Yeah. Any other questions?
All right, so time here is like some sort of training epoch, basically.
No, not really. No.
Because it's like, okay, I guess I'm just thinking of this like notion of you have to start from white noise, that's your X naught, and then
Yes.
it gets sharper and sharper and sharper and sharper. But that is not, those steps has nothing to do with the time variable here.
No. So, no, those steps is the time variable, but doesn't mean that during training that's what's happening.
Mhm.
Like, it is true that as a function of training, the model will get better.
Mhm.
But also, every time you want to generate a sample from your model at any given time, you'll have to solve this ODE. So it defines how to connect the two distributions, right? At any given time, at any given epoch. Maybe time is not the right word.
I mean, in the example of the stable diffusion thing, it almost feels like, so if time is going to the left, what I'm doing is if I think about things in terms of like for an image in Fourier space, I'm making it so that I'm choosing my amplitudes and phases for the long wavelength modes.
Yeah.
And then as I go to the later time. And
Yeah, you start from the higher frequencies.
Yeah, I'm feeling, and so is that just generally what's going on?
That's only happening because you start from the white noise power spectrum and you match it to something that has a, I don't know what color, but you know, that kind of power spectrum. If that changed, that wouldn't be the case, right? So it's not necessarily the case. It only happens to be so because of the power spectrum of X1 and the one of X0.
Right, okay.
The frequency distributions they have ends up being that way. So these models become like autoregressive in frequency when you choose that X0 and that X1, but that's not necessarily generally the case.
Okay.
Right, so the things we've done with these kind of models is to learn this kind of marginal likelihoods, right? So you can do it for density fields. So this is an example from very small scale simulations like hydrosims, like 25 milliparsecs of range, different cosmological parameters, and an example from point clouds as well. So you can do the same thing, except from a density field or image for a point cloud where each point is a galaxy, for instance, in this particular example. And the idea is that obviously emulations is extremely fast. So you can get one of these density fields in like 6 seconds per simulation versus whatever to the hydrosim, right? So this is the total matter distribution to account for the effect of variance. So obviously they're extremely fast. Now the idea is like they can also be used for inference. So if you want to get to the posterior, you can take your learned likelihood, right? Your probability of field given the parameters and just sample it. Now, it can be quite fast because it's differentiable, and you're only sampling a small number of parameters, right? Theta is lower dimensional than X, much, much lower dimensional. So this is actually quite efficient. Now, the second thing you could do is actually to learn the posterior directly. So this is what I was referring to as compression, right? So you compress your field and learn the posterior directly. Now, how are these two approaches completely equivalent? Well, the answer is not really, because they react very differently to out of distribution data. So this connects to the question that Matthias was asking, right? Like, well, okay, we have the simulators and full models, but we know they're imperfect. How do these models react to model misspecification? And this is an example of if you try to predict sigma H from these density fields with either the posterior model or the likelihood model. First of all, if you use the raw data, so the in-distribution data, they behave very similarly as you would expect, right? Now, if you add a tiny amount of noise, then the posterior model becomes biased very quickly, right? So this is a very small amount of noise that would not change the power spectrum, but it would definitely bias your sigma constraints because the posterior model, well, if you think about it, for instance, let's say that you want to classify cows, okay? So you train a model to classify cows. So maybe the model learns that cows are always on grass, right? So it can latch on into that spurious correlation because it was on your data set. However, if the task for your model is to generate a cow, right? So a likelihood model, then it is much harder to latch on to spurious correlations, right? Because you have to learn how to generate the face of the cow, the shape of the cow, right? Not just the grass. So these models end up being more robust when you learn the likelihood versus when you learn the posterior. So you can keep adding noise, right? And yeah, these posterior models can be very, very non-robust, right? To very small amounts of model specification, so it's definitely a danger to be aware of.
The previous figure that you showed was at fixed phases. So is this also at fixing the phase to the?
You mean?
Well, sorry, one back. When you were showing this, so that.
That's just for showing.
Okay.
Yeah, for big
But it's not something that's actually.
No, it's actually being marginalized over. Yeah. Right. So, okay, so we have ways to avoid having to do field level inference, right? If we only care about the cosmological parameters. So why do I still think that field level inference is something interesting to do? Well, first of all, I think it's pretty cool that you can reconstruct all these latent variables using simulations directly, right? Like the underlying black mass field, its formation history, especially for the local group, right? You can say something about formation history, particular velocities as well, right? To measure distances into the nearby universe. Now, another interesting potential application is constraining the physics of inflation. If we can reconstruct the early universe, if the likelihood is strong enough in particular, then maybe we could do more like template-free searches for primordial non-Gaussianity, for instance. So it is true that our simulators would be using Gaussian initial conditions, but if the likelihood is strong enough, even of the prior being Gaussian, maybe we can still do this. But still, an open question, right, for current generation of galaxy surveys. Now, what I think is very interesting is what we were discussing earlier, that this test of cross-validation where I fit one of my data sets like galaxy clustering, and I predict cross-correlations with other data sets is extremely interesting because you're doing this basically without cosmic bands. And it'd be cool to see how it fails, right? Because obviously it's a very hard problem. And I think another interesting area of development is either data-driven subgrid models, where you're using your constrained initial conditions to learn something about the astrophysics of nearby objects, but also people thinking whether we could learn something about missing systematics in our analysis as well. So we parameterize some systematic maps. So let's say we add the function of dust maps that people have generated in the past to our field level inference framework. We could then constrain those parameters and see if that is actually a measurable effect. Or we can hypothesize there is some not correlated systematic with the density field. How strong will it be? And is that coming from my instrument? Where is it coming from? Because you get the field level systematic map, maybe there is something that you can pull out of it compared to when we do summary statistics. So I think there's still a lot of very interesting things to do with field level inference. It's just perhaps not cosmological parameter inference. Right, so what we did in the past is compare explicit sampling of these initial conditions and cosmological parameters to the simulation-based approaches with machine learning. So in this case, we went for a simple setup, so using particle mesh, black matter simulations, and a Gaussian likelihood so that we could compare the two, right? Because, well, yeah, doing this with galaxies is extremely more involved, also for explicit sampling of the initial conditions. So in this case, we have a model that learned the posterior, the joint posterior of initial conditions and cosmological parameters given some observed field. So this is what happens to the cosmological parameter posterior. So this is comparing, so if you look at the gray, that will be just Hamiltonian Monte Carlo, so explicit sampling of a known likelihood. Whereas in the purple, we have the constraints from the learned model. So they're very, very close, right? So this means is doing a very similar job.
I don't see the bodies.
Sorry. Gray is here, and purple is on top. So the blue one, don't pay attention to that. That means if you know the initial conditions, right? Whereas the other two is if you're marginalizing over the initial conditions. I honestly don't remember why I plotted that one, but yeah.
Sorry, what should I take away from this problem?
Right, so the explicit sampling, when you know the likelihood, and implicit sampling do agree. So the model is doing a good job, at least at sampling the cosmological parameters, right? Now, doing this kind of implicit inference is more powerful because you don't have to assume a likelihood, right? Whereas for, obviously, to explicitly sample the likelihood, you need to know the form of the likelihood. And this for galaxies is actually challenging, right? So if we want to do this for galaxy clustering, it is useful to have methods that don't need to assume a likelihood. Now, the full model that we use does not need to be differentiable. Whereas if you want to make sampling 10 to the 9 parameters efficient, you better have a differentiable forward model. The problem with differential forward models is that usually they're very simplistic. All the ones we have are extremely simple, like particle mesh with some simple bias models. Halo finding is not differentiable, for instance. It's very hard to come up with differentiable algorithms. So I think this is a big advantage to come up. And it's amortized, meaning that you're paying the cost of sampling up front when you train your model. But then if you want to generate samples for a new example, this is extremely fast. So testing these models becomes much, much simpler. I can actually test the uncertainties of these models, whereas if I have to do this with an HMC, it's not good for the planet. How does it look like for the initial conditions? So this is one example, a 64 cubed resolution where you have your true initial conditions and the final field generated by particle mesh. And this is how the samples look like, right? So you have the reconstructed initial conditions and what happens after we run the full model, right? So the final reconstructed fields. Now, the model is actually doing pretty well, right? So it's getting very close. But if you look at the very high density peaks, like let's look at this one, for instance, there is a lot of dancing around, right? So this is a bit weird. So the model is definitely making some wrong approximations around here because the likelihood of these regions is extremely high. So you should definitely learn to pinpoint them in a way, right? Like the HMC would always find the IDC peak, right? Because they're just so dominant. Whereas here, you can make a 1 pixel error on them. So these are things that we're still thinking about how we can improve this by making the model more aware of the forward model itself, right? But these are things that still need to be figured out. But it's getting very, very close. Maybe more qualitatively, so here, quantitatively, you can look at the cross correlation between the recovered initial conditions and the true ones as a function of frequency, and the same for the finals. So when we look at large scales, everything seems fine. Comparison between HMC and SDI, so they do agree. But in this high resolution example I showed you, what we find is that although the model finds a very high correlation with the true initial conditions, once you run it forwards, it's actually not that good. So it's making correlated mistakes on the initial conditions that seem very small, but that once you run them forwards, blow up.
So they make mistakes in the final. The final is not as good.
That's right. Yeah, the initials is looking very good, right? But the finals is not as good.
Is there any chance to iterate, or is that too time consuming, or do things just diverge?
No, it is possible. So these are the kind of things that we're thinking about right now. So how do we make it more aware of what happens once you run it forwards, right? Now, you don't want to be doing this at training time, so it's not straightforward, but yeah, it looks like there should be ways of correcting this because you're really very close.
Yeah.
Right. Also, these are very small scales, so I don't know how much we care about this in particular. So we're also testing this for galaxies at, let's say, something that we will do for DESI, for instance. So I'm not sure how relevant this would be, but for small scale problems, which I think are very interesting, this is something definitely to take into account, that you can get very good reconstruction of the initial conditions because your metric is on the initial conditions, but then those mistakes can be correlated in a way that gives you bad match to the finals. That will never happen with the likelihood model, right? Because the likelihood will really penalize you for that. But a posterior model can make this mistake.
So what are you plotting, like what are the top and bottom?
Right, sorry, these are two examples. So one where you have like a large scale box with 32 qubit resolution. So this is kind of looking at large scales. And this is a different example where you're looking at a smaller scale. The
The y-axis is,
This is the cross correlation coefficient between the true initials and the recovered initials and the true finals recovered finals. For both Hamiltonian Monte Carlo, you know the true likelihood, and a model that doesn't know anything about the likelihood.
I guess I'm curious, if you use the generative model, linear theory or the Zel'dovich approximation, conditioned on the initial conditions that you infer from each of these algorithms, how does the finals curve look in that case? So you're basically saying, oh, let me assume that I can get the initial condition correctly from this, but I actually only want to recover the large scale displacements anyway, or the parts of the density field that come from those, because those are the interesting ones. So I don't need to use my generative model or my simulator. Let me just do one ZA time step. How does that look? Have you done that check? Because if you like get the right initial conditions, I don't know what redshift this is, but if it's 0.5 at k of 1, you're going to get essentially, I think, the same cross correlation coefficient that you're seeing here with the SBI case.
What do you mean? Because I mean, here you're running an HMC with a rifle model, right? So you couldn't get.
But for the
What do you mean?
the SBI specifically, the HMC.
Oh, you mean if you start from Zel'dovich and then correct control of that? Or?
No, I'm saying like you have your IC reconstruction from the SBI, and then you Zel'dovich run that forward.
Oh, you mean you'll get similar finals?
I don't think it'll be similar to finals, but I think it'll be similar to SBI or better than SBI. So I'd be curious.
Why do you think that?
Because the cross correlation coefficient between ZA and N-body at redshift 0.5 tends to be about 80% at k of 1, which is what you're showing the SBI curve here.
Right. Yeah, it is possible.
I mean, I'm just curious if you did that check against a forward model that we sort of more easily.
Right, but why would well, this particle match simulation is very cheap, right? So that's why I could these plots very easily. But I think, I'm not sure that will tell us much, right? Like we already know, yeah, it's making mistakes in the initial conditions that don't seem to be heavily penalized by comparing to the true initial conditions. But that once you run it forwards, they're correlated in such a way that they don't match the finals.
So when you're fitting the SPI model, you're trying to, the cost function is,
It's on the
do I
initials.
get the right initial conditions? But
Exactly.
it's not, you're never running it forward and also paying a price for, I don't come back, whatever I said.
Exactly. So what we're trying
Why?
to, because it's expensive. Especially, let's say we want to do this with full body or hydro simulations, right?
Okay.
So I don't want to be doing training, generating those forward simulations.
I guess that's what it's, you could make a penalty with something
Yes.
cheap, going back cheap.
So right now what we're building is like fully invertible models. So you can either go from initial to finals or from finals to initials. So you can use the feedback from the model itself without having to run like surrogate, right?
So
Because otherwise it's too expensive.
Is the expensive part here, like the particle deposition step, that one's on,
What is the running the simulation, like running the forward model?
but like I guess if there were some sort of like Eulerian solver, it's easier to see how it would be fully differentiable at all steps, if you're not like tracking particles and then putting them down. Is that the step that's difficult, like that makes things challenging?
Well, it's running the full model, right? If you want to correct for this back and forth. like if you have an embodied simulation, yeah, first of all, an embodied wouldn't be differentiable. Like here, we can do it because particle mesh, so it's differentiable.
I mean, particle mesh is also involves particles, right? Like it's also Lagrangian.
But on a
so-
mesh, so you can actually make it fully differentiable. That's why you can run the agency, right? But it's still too expensive to train on that. But a surrogate might be the right way to do it. But we'll see, right? There's an open problem. Now you can also look at how it looks like as a function of training simulations, right? So this is, if you look at the area under the curve of these cross-correlation coefficients, right? So how much overall cross-correlation you have from different scales, right? And you can compare the Hamiltonian Monte Carlo, so what the SBI should converge to SBI, right? Basically you see them converge at something like 10 to the 4 simulations. I think for these examples, so it doesn't mean you will generalize to more complex formal models, but it's not too bad of a number given how costly sampling is, right? So to get one chain of HMC, you probably need around that number of simulations anyways. So this would be fully amortized.
Kind of crazy. Can we predict that number accurately?
Yeah, that's a problem, right? Because you don't know, if you don't have a reference that you won't have, because you don't know the likelihood, for instance. So if you have a much more complex formal model, you won't know.
Like, there must be an answer, there's some amount of information that you have to learn. I mean,
Right, but also how efficient is your information, your algorithm at learning that information matters as well. So I don't think you can separate the two. Yeah, that would be nice. Sadly, I don't think so. I'm gonna keep track of time. Okay, so I'm extremely late. So okay, never mind. Let's continue for a few more minutes. So okay, so can we do this for density? Am I gonna show you some results on density? Well, no, it's not straightforward, but for different reasons, right? First of all, obviously, small differences in what we simulate and what we observe can cause huge biases. So we want to get as close as possible, right? So we want to actually incorporate survey systematics. So what is it, what the survey actually sees, and how do we actually put it into our simulations, right? So these are some of the annoying things that we actually have to deal with. But of course, the most annoying one is probably what some of you actually really care about, which is what's going on with galaxies, right? How do they form and how do they actually populate the cosmic web? So everything I showed you was mostly on dark matter simulations, right? So how do we take this forward? And an additional challenge is scaling this up in volume. In particular, I'm going to focus now on ideas coming from hydrosims, and obviously scaling that up in volume is very, very difficult. And it's not just because the simulations are expensive, but also in terms of memory and storage, we're really running into problems. So I think an interesting question is whether EFT can help us do this, so we can have hybrid simulation-based models and EFT on large scales to actually make this problem practical. I think this is an interesting question for this group. Okay, on galaxies, so let's finish with that. So obviously, it'd be really nice to have a self-consistent model of galaxies and gas. In particular, if for field level inference, if we want to do this kind of cross-correlation studies, right? We want to look at, once we infer our initial conditions, how do our simulations correlate with, let's say, TSZ, for instance, or KSZ, or any other effect that actually looks at gas distribution. So it'd be great to have self-consistent treatment of gas and galaxy formation, right? Now, obviously, the closest we can get to that is hydrogen. Closest because obviously they're not perfect, but at least they are trying to simulate this self-consistently. In particular, we want to tackle like multi-wavelength observations, right? We want to use data coming from FRBs, Sunyaev-Zel'dovich, etc. We really want to do this self-consistently. Now, the way we've been thinking about scaling hydrosims is by using this kind of panels-like simulations where you take in different subgrid prescriptions and varying its parameters, in particular looking at the strength of AGN feedback and supernovae feedback and varying it at scale, right? So you're basically generating 1,000 boxes with varying astrophysical and cosmological parameters and running them forwards on very small volumes, right? These are slowly growing, but very slowly. And the idea is that we're going to match particle mesh simulations. So we're going to start from density fields and velocities coming from particle mesh. And we're going to learn models that can predict the baryonic fields based on that. So we've been doing this in particular for Lyman alpha. So using gas density and gas temperature, emulation of gas density and gas temperature, but obviously we're working on doing this for galaxies as well. So our current model optimized for Lyman alpha works at the field level up to like a Kmax of like 10, so pretty small scales, and it runs very quickly, right? So it's like about 7 GPU minutes for a 50 megapascal simulation. And what's interesting about this is because these models are fully convolutional, you can scale them up in volume, right? You can train them on small simulations and deploy them on much larger simulations, right? You can run your particle mesh on a much larger scale and run these corrections on top to get to much larger volumes. The test we've done currently is going from 25 to TNG50, right? And that still generalizes quite well. The assumption is that this mapping is actually very local, and the most that you're missing will be carried out by the black matter large scale simulations. That is the assumption here. But we'll see how that works for galaxies once it's. Okay, but finally, let's maybe finish with this. So obviously, okay, we can do this for one particular subgrid prescription, let's say TNG, but we know TNG is not the right answer, okay? There's making some assumptions about how AGN feedback and supernova feedback work. And if you vary those assumptions, you get very different answers. So this is also an outcome from Camels, where they look at different subgrid prescriptions like Simba, Astrid, Magneticum, and the gas temperature and gas density as a function of redshift, starting from the same initial conditions. And you can see that these models can look extremely different, right? So there's a lot of uncertainty about subgrid physics that we would like to marginalize over versus just being like, okay, TNG might be the right answer. So Ming, a student working with me that is actually visiting for the next few months, so he'll be around as well. He's been working on this idea of learning a continuous representation for baryonic feedback. And the idea is where we can learn to generate baryonic fields based on the dark matter and some continuous representation that we learn. So this would be like equivalent of the bias expansion, but on very small scales. Kind of try to make it generals, like it won't be subgrid dependent, and that we can constrain. So then you can marginalize over all this more general subgrid prescription, interpolate between different simulators, for instance, as well at the field level, and maybe learn something about baryonic physics by constraining the Z representations with multi-wavelength observations. Now you train this on these different suites of subgrid prescriptions, right? So here we're using TNG, Simba, Astrid, and Eagle with different variations of supernovae and AGN feedback. And you're learning to encode these different fields into these low-dimensional representations of the order of 10 parameters here, like 10 to 50. And then you learn to decode. So the Z variable has to capture information that is relevant to do this mapping from dark matter to observable baryonic fields.
So you're training on all 4 simulations?
You're training all of them, yeah.
So in principle, you're also learning the feedback prescription.
Yeah, exactly.
Different.
That is different from. So this is, for instance, how it looks like in 2 dimensions. So we project the Z representation in 2 dimensions. Each point here is a different simulation. And the idea is that, yes, simulations coming from the same subgrid prescription tend to cluster together. So it covers information about what simulation it came from. There is some confusion, right? So some of them do look similar to each other, and there's certain parameter values.
But it's the idea that things that are in between these points probably are similar enough, and we should, when we marginalize,
Yeah, that's a hope.
that it explores all of the space of possibilities.
Right, that's a hope. So for instance, here we did a test where we left one of the simulations out, Magneticum, that includes magnetic fields, right? Otherwise, I think it's similar to TNG, to see what will happen, right? Will the model still work? So, well, first, let me show you one example of how you can interpolate. So if you take one of the Astrid simulations and look at its Z representation, and take one of the Eagle simulations, you can now interpolate in this latent space and look at how the outcomes would look like in terms of like gas density and temperature, for instance. And you can see that it's continuously varying, right? So it's not too insane to think that it's actually interpolating between the two.
So, but this C space is, you don't know, you just specify a number of dimensions that is spectrum, and the thing is trying to encode in some continuous variable in the number of dimensions, something that goes from one.
That allows you to figure out that mapping. Yeah, you could add some like scale dependence, for instance. So there's things that could be added, but right now there's nothing in it.
Is it profitable to try and understand the structure of that space?
Maybe. Yeah. Ideally, yes, right? So that you can constrain it and say something about.
Presumably, there are some choices that are like a little bit random in the sense that you
Yes.
could have represented the same thing with 10 dimensions, some other coordinate.
For sure.
So.
The basis, it doesn't matter, right?
But if you project it,
Yeah.
yeah, but I mean, it's like a primary component.
Yeah.
Yeah.
It would be something like.
That's why you make this like Disney plots, right? But yeah, it's. But again, in terms of generalization, it actually works surprisingly well. So this is an example from magnetism that again wasn't used for training, right? And you can look at the cross correlation, for instance, from stellar mass maps from true and predicted, right? As a function of the scale again. And you can see that magnetism actually has very similar features to like TNG that was used for training, right? So you're extracting the same amount of information. Same for gas mass,
So meaning that it lives in the Z space, you can go somewhere else and it will look like that one, even if you didn't use it for the training.
That's right. Of course, there's no guarantee, right? It works for this example, but at least is promising if it works.
I guess you're doing this always in sort of skill space, you're looking at distribution of stellar masses and simulation. But can you also sort of look, is there a notion in this like interpolated space of what is a galaxy in that model even? Like if you zoom into an overdensity.
Yeah.
Like the galaxy in TNG had some set of subgrid physics for what is it doing when something falls in and gas falls out? That is like completely, there's no way to interpolate between what that physics is doing and what the Simba physics is doing.
Right. Yeah, I think to that extent there's no hope, right? That's why on larger scales, the way gas is distributed, there should be a more general prescription that is independent of like how anisotropic is a distribution, how far out does it go? Like we're looking for the more general descriptions over larger scales. So it is really more similar to like bias expansion, but not conservative and on very small scales. We're looking for broad characteristics that you can store in the Z variables, but not so small scale.
Is the reason that this is doing fairly well because these simulations are similar, or like if the simulations were very different in how they worked, would you expect to see more variation?
Right, yeah, I'm not sure. Like Simba is definitely extremely different from the others. Like you can see in the video, right, how it blows up super quickly. So that's probably the most different one. Now we haven't done the test of what happens if we leave that one out. I think that would probably not work. Like basically, it's extremely different. I mean, latent space, you always see it come out as special, right? It's maybe too different, but I don't know. It's a good question. Yeah, how
They were all run with the same seeds or not?
well, the seed is varying as well.
I know, but the same seed was run with the different prescriptions, so.
Yes, yeah, that's why we can do this example, right? For instance, this same seed.
You need that to be.
No, you don't need that. You need that to make this plot.
Much longer for you to figure it out, for the thing to figure it out.
I don't see it will be much because it's conditioned on the backmass field, so that already has all the information on the seed, right? So actually, I don't think that matters. Okay, I think I'm gonna completely skip over the second half. That was more on the idea of how do we actually use simulations and observations to do more robust simulation-based inference, right? So it was related to Matthias' question of, okay, if we need to have a perfect simulator to make sure that our inference is not biased, what is the hope? But I think there is some hope if we think about how to align these spaces, right? Simulation and observations. But yeah, we can chat more about this, whoever is interesting, but yeah, it has some very toys examples of how this will actually work. But let's just finish here with the first half. Thank you.
We've had 50 questions, but we have time for a few more. Are there any? I can ask one maybe. I think you did sort of allude to this, but so you're always learning in these Camel's boxes, which are 25 megaparsecs, but you're learning something about, presumably you're learning what gas is doing, at least out to those scales. Can you then run a n-body sim at a different volume, say like a gigaparsec, and then run one of these models to sort of paste the gas distribution on, or are they sort of limited by the fact that they've been trained on 25 megaparsecs only?
No, that's a hope, right? So we've done this for the Lyman alpha example recently, where we trained on 25 and then tested on GC50. That's live volume, also high resolution, and that actually worked really well for Lyman alpha, which is relatively big, so it's big. But yeah, the hope that we can do this for other observables as well.
but it's not something, it's not an architectural limitation.
It's not actually because it's fully convolutional, right? So you can, I mean, memory-wise, things like become painful once you get to 1 GeO classic, right? But I think the goal we established at the beginning was to go like to Millennium TNG, it's 500 megaparsecs of range, and make like versions of varying cosmologies and varying astrophysics of Millennium TNG at that volume using Hammond's, right, as a training set. So I think that is the roadmap right now, like use particle mesh conditioning to scale up in volume.
Yeah, so thinking in terms of my MHD stuff, where I don't know how true the assumption of locality, which I said, how easy is it to use these as subgrid models?
Right, so I think a very interesting question is something that I haven't really talked about at all, because this is post-processing, let's say, right? But yeah, you could learn a correction to your force, for instance, right, during training. Now, you need a differential form model, which you might have, I don't know, but it's not straightforward, right? Because during training, you need to propagate those gradients through your form model. So that's the tricky thing, right? But yeah, that's another, I mean, that we're working on, like whether we can make like probabilistic force corrections, right? Let's say you take a particle mesh simulation and you add a force correction that is a neural network and maybe probabilistic. And then yeah, try to fit it to higher resolution simulations, for instance.
I guess this is a little bit. Let me just push back on all these things, right? So again, whatever you're training this thing, you're working always in the direction, it's a black box, I have some black box, I'm learning similar, I don't need to know. Why? What's the point of this whole thing? Because we really need to want to understand, like even measuring some cosmological parameter, useless, who cares? I want to understand why I get this number. Especially because I need to know it's robust. And understanding is solving some differential equation, it's doing physics. Even if you get the right answer, irrelevant. I mean, who cares? I mean, maybe for some applications, but for us, don't we need to understand why would we want to go in this direction when we are guaranteed to know what the heck is going on? Like somebody, alien tells me the answer. Okay, I wait for alien to tell me the answer, but that doesn't give me anything.
Right, my point of view is that having an oracle is still helpful, right? If I can tell you that A and B are connected, I might not know how, but that's already interesting, right? Then you can go and understand. But first, let's find something interesting. So far, we haven't found anything interesting. So once we find something interesting, then I think, yeah, let's understand, but let's get there first, right?
We haven't found anything interesting, I have lots of things.
Sure. I mean, in the recent history. But I think, is it true that, so that's why, so the thing that I didn't really have time to explain tries to go in the direction of, okay, let's say that we have put all our physics knowledge in our simulations, right? And now we have some observed universe. Can we say something about what information do they share and what information they don't share so that we can improve these forward models, right? In a way that is interpretable. But yeah, I think there are ways of thinking about this, how more the connection of like, what makes them different and what makes them similar. By the interpretation will always be hard, right? But at least if you have some way of doing this out, right? I think that can be helpful. So I agree with you to some extent. To some extent.
In the midst of a richly informative talk, you said something that sounded a bit like magic, which was that the initial conditions are Gaussian, but as long as the likelihood is strong enough, you can find evidence for primordial non-Gaussianity.
Right.
Does that work?
Yeah, this is a hope, right? I'm not sure, but I mean, you can have a Gaussian prior, but your initial conditions won't necessarily be Gaussian. And actually, this is something that can happen because of model misspecification as well, right? If your likelihood is strong in some regions, the prior won't matter, right? So people have found, for instance, very like skewed initial conditions in Borg, for instance, and they have to do like really, that was really magic to get them to be Gaussian fields, right? So if you can make sure, the problem is that model misspecification will be conflated with that, right? But in principle, if the likelihood is strong enough, you should be able to do this as well. Just measure the bispectrum of your reconstructed field, right?
Probably a week prior on initial conditions, right?
The week prior, yeah. from how constrained the field is at the field level, right?
We can keep chatting over lunch. Let's thank Carol again.